Hello and welcome to the latest of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Neil Dennehy, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be moderating today's webcast. The idea to have these hour-long webcasts originated several years ago with the members of the NESC GNC Technical Discipline Team, or TDT, who thought this would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community of practice and others. I'm now very pleased to introduce today's speaker, Mr. Aie Cella. Aie is an aerospace engineer with 2 decades of experience. Early in his career, he served as a flight controller for the International Space Station. He later found his passion in spacecraft autonomy design. He has designed supervisory logic for satellites and worked on an electro-optical sensing system for crewed rendezvous and proximity operations. He is currently a space segment manager at MathWorks, helping space programs around the world reach their goals using the latest engineering tools and practices. Aie's talk today is entitled The Evolution of Digital Engineering, Future Visions for GNC Model-Based Design. His talk will present a vision of how digital engineering, including the careful use of artificial intelligence techniques such as machine learning, can meet the increasing future expectations of higher autonomy, capability, and complexity in space systems, especially for GNC applications. Aie will discuss how digital engineering, incorporating a model-centric design approach, has the potential to increase both engineering efficiency and mission performance. And he will present the current state of digital engineering adoption and some common limitations. And at this point, I would like to turn the webcast over to Aie.
Thank you very much, Neil. Pleasure to be here. Now, most of you have probably experienced firsthand through initiatives, or at least heard about the current push towards digital engineering. And today we'll take a look at the role that the GNC discipline in particular has in the digital transformation efforts going on in our industry. We all recognize that today's programs are getting more complicated and more ambitious all the time. And at the same time, we see competition driving down costs, which naturally leads to an expectation that these more complicated systems are developed more efficiently. Now, as the systems get more complicated, the answer is we need better systems engineering. That's not optional. If that doesn't happen, the systems will fail. However, I would argue that traditional systems engineering is difficult to perform well at the scale and complexity that space systems are evolving towards. And there's a key collaboration that needs to happen with subsystems engineering and GNC in particular, as we'll discuss later. Now, I'm going to preface this talk by saying that this content is really geared towards what I'll call high integrity systems. Driving down costs on tech demonstrators or programs that have a large risk tolerance is a simpler proposition. Where it gets really interesting and tricky is our big important programs. And the working definition I'll use for a high integrity system is simply one where our risk tolerance is low. So that implies high value assets, including perhaps crewed spacecraft. So this presentation talks about digital engineering in the space industry as a whole and the GNC discipline specifically. First, we'll take a kind of a background look at how GNC plays a critical role in the system level design of space missions, and that'll set the context for the digital engineering discussion. Next, we'll take a look at model-centric design, which is a subset of digital engineering and enabled by it, which has exploded in popularity over the last 10 years or so. We'll take a look at model-based system engineering and model-based design, and explore how the two could be merged to realize a more complete form of digital engineering than what's currently the standard. And finally, it's hard to imagine a digital engineering talk these days without mentioning the role of artificial intelligence and machine learning and deep learning specifically. AI is slowly but surely creeping into our industry. We'll highlight how and where it's being used, and some of the current challenges and directions of future research. And again, because we're dealing with high integrity systems, we'll interleave this talk with considerations for verification validation, or V&V. So let's dive in. So I once worked in a department called Flight and Controls, whose engineers were generically referenced as Attitude Control Subsystem Engineers, or ACS. Yet despite the name of the department, one of our key deliverables was the Algorithm Description Document, or ADD, which defined every algorithm running on board the onboard computer for every subsystem. Now, how can that be? Well, there are a couple of reasons. First, ACS and/or Guidance Navigation Control, GNC, is incredibly strongly coupled with other disciplines. We can look at a simple example to kind of highlight that. On the left of the screen here, we see a spacecraft. And on the spacecraft, there's a valve. Now, the valve is by nature a mechanical system, but in this instance, it's also part of the propulsion subsystem, since it actuates a thruster. Because the valve is electronically actuated, it's also a part of the electrical subsystem. Because it's commanded remotely, it's also part of the command and data handling subsystem. Because it moves a vehicle, it's safety critical and part of the safety folks' concern. And of course, there's the operations consideration. The operators are the ones that'll actually actuate this. So all of this for what's really fundamentally a GNC, or attitude control enabling device. So that talks to the coupling. The second reason that GNC is so important in our flight software systems is that early onboard computers and software were really mainly driven by GNC requirements. Over time, other subsystems became included, but GNC continues to have a fairly dominant role in onboard computing. And onboard computing these days really orchestrates everything at a system level. Now, despite the interconnectedness of our systems, the truth is that engineering today, for the most part, still can remain highly siloed within domains. I worked on a program where I had to interface very closely with subsystems engineers that actually worked for the same company I did, had a direct interface to my system. Yet if you looked at the org structure, we met at the program manager. So obviously there can be structural and organizational challenges to working seamlessly together, because these two groups, of course, had different budgets, different schedules, and those all had to be negotiated. Now, I also worked on a clean sheet design where this problem was recognized early on. And the program put all of the engineers in one large room so that they could all work together and sit next to each other and report to the same people. And even though the physical environment was set up in a very collaborative way, I found that instinctively engineers would still put their heads down and work on their own systems. So there's both an organizational and a cultural tendency to work within these silos. Now, making sure that things work at the system level, of course, requires system level thinking. And systems thinking, as I call it, requires breaking down the silos. What I mean by systems thinking is considering the interconnectedness of all the components in the system. And a fundamental concept of that is that a component can behave quite differently and sometimes in unexpected ways as part of a system than it does in isolation. You can think back to the valve example, right? On its own, it just opens and closes. But in that particular location on the spacecraft, it moves the vehicle. Now that's a pretty obvious example. We could imagine this comms antenna, right? Where on its own, you think of it as enabling communications between the spacecraft and the ground. But if you look at it a level deeper, it does more. It actually drives requirements for GNC pointing, was one thing. And as soon as you deploy it, it actually happens to be a disturbance generator for GNC as well, right? It creates drag, it accumulates momentum. So it's a momentum accumulator depending on your role. Now, those two simple examples showed how one component affects multiple subsystems. We'll take a look at a slightly different angle through a program that I used to work on, ISS. Of course, when I worked on it, it used to look like this. And as some of you recall, back in the early days of ISS, we had the luxury of being able to choose what attitude we were flying, which of course leads to the problem, a systems thinking problem of what attitude should we fly. There's multiple considerations that go into this, right? You want to minimize your drag in order to minimize propellant use. You also want low momentum accumulation, so you're looking for a drag balanced attitude. Crew safety is paramount. You want to minimize exposure of the pressurized volume cross sections to the velocity vector to minimize the chances of a orbital debris strike. You have to be power positive, so there's the optimization of the angle of the solar rays to the sun you need to consider. It has to be thermally acceptable to ensure components don't get too hot or too cold. Actually, even to prevent expansion or contraction of the metallic structure, which could be a problem. And of course, you have to maintain communication. So you have to point the antennas at the teeter satellites for the ground. Now, all these trade-offs are interconnected. This type of problem can't really be solved by a GNC specialist alone. It requires multiple subsystem input and systems engineers who are system thinkers. Now, systems thinking has a very, very important cultural aspect to it, because systems thinking requires access to knowledge in order to actually work with that knowledge and synthesize this. And there's a couple different types of organizational culture when it comes to sharing that knowledge. One, which I'll call a tribal knowledge culture, is one that hides and hoards information. And by the way, sometimes it's not trivial to tell what type of culture you're in, because I have worked in some tribal knowledge cultures that have actually been very highly regarded from the outside because they're perceived as the system experts. But some ways to tell might be asking yourself questions like, how easy would it be for somebody else to do your job if you didn't come to work one day? Are there a lot of undocumented tricks and tips that have to be known and understood before you can make things work? Like, oh yeah, you have to skip that step in the procedure. We just haven't documented it yet. Now, these types of cultures are easy to unintentionally develop because there's false rewards associated with them. Again, you can develop this perception of being an expert or highly skilled at something that nobody else knows how to do. Now, an information sharing culture, on the other hand, exposes and shares information. It rewards things like simplicity over complexity, which just means that things that really should be easy actually are. It tends to reward team output versus individual output, which enables individuals to learn each other's tasks. And it rewards transparency, like clear documentation. And one thing that this all does together is it helps make work accessible to people outside of that group. And again, making that knowledge accessible is a key to be able to think and perform engineering at a systems level. So maintaining an information sharing culture takes some effort because it can be perceived to be at the expense of the individual when it really is benefiting the whole. Now, I mentioned earlier the connection between GNC and software. Software issues, of course, were recognized very early in the history of spaceflight. This image is from Apollo 11, which of course, in hindsight, is an unqualified success. But many of us also remember or have learned and recognized the infamous 1200 series computer alarms during Apollo 11, which rebooted the LEM guidance computer multiple times during descent. And this actually encouraged NASA to address the software engineering approaches used in the agency, and eventually, as a result, led to the NASA procedural requirements that we have in place today. Now, over time, this has led to a process which has become very document intensive. And by over time, I mean many of the processes that we follow today trace back to failure investigations of the past. and they're there to prevent something bad from happening again. This is especially true of organizations that have been around a long time and have a long history. And as a result, we've defined construct for ourselves like gated processes, change control boards. And this, of course, is necessary, right? It's a good thing. But at the same time, it's challenging to get right. And that leads us to a discussion about model-centric design. I would argue that our industry is undergoing an evolution. In the beginning, we were very hardware-centric. That's the picture on the left. But we recognized quickly that the hardware was becoming too complex to control without software. And in fact, when I was working on ISS, there was a running joke that said, the space shuttle had just enough software to run all the hardware, whereas space station has just enough hardware to run all the software. And to a degree, that was true. And honestly, many organizations are still coping with how to deal with our transition to becoming a software-centric industry. Now, more recently, we've seen a trend towards model-centric. And this is happening kind of for the same reason. Our systems, including our software systems, are simply becoming too complex to understand without models. Models can give us a way to explore systems before they actually get built. And they can also give us a way to provide abstraction from the system for understandability. And they can have different views that promote understanding. And when I talk about models, it extends to very simple models. For example, here we see two different views of some entry, descent, and landing logic. For software engineers, looking at the code-centric view on the left might be the right place to live and be. That's their domain, that's what they understand, that's where they live. For an algorithm design engineer or a systems engineer, looking at the model might be more intuitive in order to understand what's happening. Now, digital engineering as a whole is becoming very much acknowledged by the agencies. If you look through the NASA Human Landing System requirements, right up front in Section 2, you'll see in print a stated objective of the program to advance towards a digital engineering environment and away from the traditional document-based approach. Likewise, ESA in their 2025 agenda says that the European Space Agency will digitalize its full project management, including, by the way, for procurement and finance. And it's not shown here on the slide, but it's worth mentioning that just last year, JAXA updated their space software development standard, and a notable change in the latest release is specifically addressing model-based design and automated code generation techniques and considerations. So this is, this is something that's becoming very mainstream. Now I'm going to focus on two main subsets of digital engineering. The first is what I call model-based design, or what we at MathWorks call model-based design. It's a design practice that's becoming more and more common among subsystems engineers, really especially within GNC. I would say GNC are probably the trailblazers in terms of implementing model-based design. And the other is model-based systems engineering, or MBSE, which is the most widely adopted modeling construct among systems engineers. I'll start with model-based design, which is well adopted already within GNC, like I mentioned, particularly in Europe and North America. And many of you are already using model-based design for components and subsystems, and even using model-based design to rapidly integrate with hardware for rapid prototyping workflows. And some of you are using model-based design to automatically generate code straight out of your models, whether it's production flight code in some cases, or maybe C, C++ source code of your plant models that you can use in your real-time test environments. So you can see that the hardware and the software domains, of course, remain very important. But the main difference is now that the model is at the beginning and center of the design process and serves as the gold reference of truth. And we all recognize that integrating hardware and software can be difficult. And for successful model-based design organizations, the model can really help bridge this gap. Because before you bend metal, you model your hardware. Before you generate code, you model your software. And in your modeling environment, you have the ability to test the two together. Now, I'd say that somewhat a downside of model-based design as it's currently practiced is that most organizations remain constrained to the component and the subsystem level in their modeling, which makes system level analysis using model-based design difficult. And that's where model-based system engineering comes in. It's also pervasive in the space industry. And the idea behind MBSE is to build a digital model and a modeling tool that formally captures the relationships between requirements, architecture, and then both the functions and the components that make up a system. MBSE can capture multiple aspects of a system, including the physical, functional, and behavioral allocations. I've personally experienced it to be particularly effective in requirements engineering, using tools like use case analysis and activity diagrams in order to start with a high-level ConOps, and out of that ConOps derive the high-level requirements for the system, and then continue to derive lower-level requirements through functional decomposition. So for example, a high-level requirement might be to image a location on the ground using a satellite. And the functional decomposition may involve things like slewing the spacecraft, activating a camera, collecting and downlinking the data, and so forth. And all of these relationships can be captured and connected digitally. Now, in the old way of doing things, where paper documents were the primary artifact, if I encountered an issue with the design and wanted to change something, I would go to a change board and the chief engineer would ask me, does this impact anything else? And I'd say, no, it doesn't impact anything else. But how can you really prove that? Oftentimes engineers with a good reputation may have found their proposals approved more often. But having a digital model that includes the relationships between the components and the dependencies between the requirements is a game changer for impact analysis. And it greatly improves the agility. In fact, in the old way, there was sometimes great resistance to change, even in the presence of defects, because of the very real worry of introducing new ones. And this applies even months or years before a launch date. So I would argue that that just the processes that we had built and the tooling that we had often led to suboptimal designs and the stifling of innovation. Now, this chart is something that I put together after I attended the European Space Agency Model-Based System Engineering Workshop back in 2020. Over the course of the workshop, a number of papers were presented, and Mr. Jean-Louis Traillon of ESA put together this nice summary that I made into chart form at the end of the workshop that highlights some of the benefits that were demonstrated in the papers. And we can see here that MBSE, as reported by industry in Europe, contributed to improved design, improved continuity, better process control, improved communication, all of these positive things. But at the same time, I'd argue that system engineering as practiced so far today is still not perfect. These are the results of a survey that MathWorks did with our customers a few years back. And we asked our customers how happy they were with the current tool choices they had for modeling system architecture. And as you can see, out of the 120 or so engineers that responded, not that many were very happy. So we probed into this a little bit deeper to find out why. And we heard from our customers that there can be a steep learning curve to use MBSE tools. SysML, the systems modeling language, which is predominantly used by these tools, is a very, very rich language, but it can also be quite complicated. It's based on UML, which came from the software world, inherits some of that complexity. And sometimes there's a temptation to get quite deep into the ontology of SysML. I've spent way too many hours arguing whether the right relationship is extend or include for a relationship between use cases that in hindsight really didn't change the design one way or the other. Now, model-based system engineering does a great job with relationships, but what we heard from our customers was that we sometimes struggle how to analyze other aspects of the design, like performance, for example. And it's actually quite common to perform trade studies in other non-MBSE tools. But by far the biggest issue reported by our customers was that there was a gap between moving from architecture to design. And the main reason for this is that most MBSE models are static and don't simulate, which of course ties in with how analyzable they are. So let's dive deeper into how digital engineering can help address some of the challenges we just identified. So to recap, we identified a challenge with model-based design that it is not usually practiced at a systems level, and we identified some challenges with model-based system engineering that relate to the integration of the architecture with the actual design. Now, I want to take a brief detour here to address a common statement we hear from GNC engineers, which is, hey, we've been doing digital engineering for decades. We know that we can't test our systems in a lifelike zero-G environment here on the Earth, so we've had digital models for decades and decades that model what we do. That's all true, but when I'm talking about digital engineering at a higher level, it applies at more than just a subsystem level. And I would argue that we've gotten very good at digital engineering at a subsystem level, but there's a digital thread that's missing between not only subsystems, but also life cycle phases. And we'll get into that a little bit more. Now, digital engineering has the potential to fundamentally change the way we design, build, and verify systems. Currently, it looks something like this, right? We design, then once the design is approved, we build the system, and then we do integration and test. And in the last phase, it's not uncommon for that to consume maybe half of the total program cost. There's a great deal of variability, but that seems like a reasonable ballpark. Now, there's a different and distinct model-based paradigm emerging in which you shift this process into something that looks more like model, analyze, and build. And I'm borrowing loosely here from Will Roper's paper, There Is No Spoon. Now, I think two things. One, there's a potential for a very fundamental shift here. But two, I think that the adoption of something like this, the move to something like this, specifically in the space industry, will be much more incremental. I don't see us giving up a testing phase anytime soon. I think that will always exist. But what we do have the potential for is we have the potential to move many of the defects that are currently found in test into model and analyze, which would then dominate the life cycle. So again, to recap the current state, we have model-based system engineering, which is quite good at requirements and architecture. Many subsystem teams are using model-based design. That's quite good at design implementation, but not at the system level. How can we connect the two? Here's, I think, where we have an opportunity for systems thinking. So let's look at a slightly different view of the situation. I'm going to put this in the context of a program lifecycle design V. utilizing a model-based environment. And I think even when we use model-based techniques today, we more often than not end up with 3 different and sometimes disconnected types of models. And notice here on the right, I'm introducing a 3rd model that I'm calling a system simulation model. Early in the life cycle, we develop architecture models using model-based system engineering. During the design phase, we have design models that are implemented in model-based design. And during integration, tests, and operations, we often create yet a 3rd type of model, which I'm calling here the system simulation model, which can be used for hardware software integration in environments like Iron Bird, for example, or they might be used in operations to validate ops procedures and train personnel. So the advantage of the system simulation model is that it actually does model at a system level, but the disadvantage is it's generated too late to actually inform the design. So wouldn't it be nice if we had a single model or single modeling environment that we could carry through all of these life cycle phases? And of course, this will require different levels of modeling to exist as well. But there's several ways this could help, right? It could make the subsystems work very transparent, because if you're all working in the same model and modeling environment and you have the architecture directly tied to the design, that gives your systems engineers access to your subsystem design to do their system level analysis. So really it expands the ability of organizations to do systems thinking in a digital environment. And it can help discover both static relationships and behavioral interactions between subsystems. So how do we get there? Well, we're already seeing that as our missions get more complicated, there's a growing interest in modeling at the systems level. I see this with our customers. And like I mentioned before, the models at the component and subsystem level may have well understood behaviors, but we still need to understand the system level interactions between these models. And in fact, that's where a substantial portion of mission risk arises, and that's where a lot of the escapes happen. So let's talk about how we could close the gap between model-based design and model-based system engineering. This is actually something that MathWorks has been investigating for many years now, based on our observations, not only in the space industry, but also other industries, including automotive and so forth. So our vision really is to have an architecture model that can integrate seamlessly with a simulation engine, which would allow engineers to expand into multi-domain, multi-subsystem simulation. And this would allow them to integrate their architecture more closely with the larger hardware in the loop test setup. So no longer, one component, one board at a time, but the larger Iron Bird type integration setups. And it would allow you to digitally trace the architecture more closely to the full software application rather than individual software units. So this is something that is primarily done in the UML domain today. Now it would of course have concepts like software architecture and system architecture built in, but integrated into the simulatable model-based design paradigm. And in case you haven't had a chance to explore it, in 2019, we released a product called System Composer, which sits directly on top of Simulink, which is our simulation tool, and allows you to design and analyze system and software architectures and do requirements engineering. And the purpose was really to help close the gap between model-based design today and model-based system engineering to realize the benefits of both as we design increasingly complex systems. Now, if we develop our skills and we're able to navigate the full realm of digital engineering along both of these axes, one of them going from component to system level, while the other one goes from hardware to model to software, we'll kind of naturally end up building or producing a digital twin. And in this context, what I'm calling a digital twin is simply a digital representation of the physical system that's so close to reality, not perfect, but close enough to reality, that it can be used in place of the real thing to do test and analysis. And importantly, it's also updated with data from its physical twin to validate the model, which is why the connection to hardware is so important. So let's kind of walk through this through an example. Let's say we wanted to develop an imaging satellite system that provided visual imagery of, let's say, MathWorks headquarters at some frequency and resolution. So probably what we'd do is we'd start out by sketching an architecture. We'd have a space segment, a ground segment, some external providers like launch. But of course, because we're doing this using digital engineering, instead of using a napkin, we would use a tool. So in this case, let me open up my MATLAB and take a look at what such a model could look like. So here we see the model. This is the same as in the sketch. And to it, now we've linked some high-level requirements that are associated with high-level components. As you'll see, the purple boundaries there show the relationship between requirement and component. And as we drill down into the architecture, we can define lower-level requirements and map those to lower-level components, subsystems now. And we can also define interfaces to connect the subsystems and assign attributes and stereotypes to those interfaces. But the key difference here between this and traditional model-based system engineering is that you can simulate it by hitting the run button. So here we see the satellite actually flying around and the system simulating. Now, if we continue to look under the hood and kind of dive deeper into this model, we'll see that what enables the simulation is that at some point under the hood, we run into a Simulink model right here that's directly linked and connected to the architecture. So whatever subsystems we've defined with enough fidelity to have a simulatable component, we can now simulate together. And further, we can actually now use these simulation results to do further analysis on the architecture and design. So here, for example, I've taken the results of that simulation and I'm bouncing them against the requirement to fly over the MathWorks headquarters. And in this case, I've used the results of the simulation in the orbit together with static parameters that I've put into the architecture that describe the attributes of some batteries and photovoltaic arrays to do trade studies for battery and power system sizing. So these are the types of things that you can do if you're able to effectively combine the worlds of simulation and the worlds of architecture and system engineering. So to summarize, the vision of digital engineering is to connect systems engineering, subsystems engineering, and even operations across subsystem domains and across life cycle phases. And I'd be remiss if I didn't highlight that digital engineering investments require not just investing in digital technologies or software, but it's important also to remember to invest in the people, to enable the workforce to be productive in the digital world. Much of this software, like I mentioned earlier, is not trivial, right? And just like I wouldn't buy my children a car and expect them to learn how to drive it themselves, we shouldn't expect to buy our workforce complicated technology without providing the training and resources to use it. Because ultimately the measures and metrics of success are people measures like productivity. Are they meeting the right outcomes? Are the milestones happening? All right, so now let's get into our final section and take a look at how AI and machine learning fits into this vision. I'll start with some basic definitions just to kind of level set. Artificial intelligence, which is the umbrella term here, is simply the capability of a machine to imitate human behavior. And I'd argue that in the space industry, it's closely linked with the concept of autonomy, or vehicles able to perform increasingly complicated tasks without human intervention. And that's, of course, been a key attribute of spacecraft for decades, but the algorithms that enable autonomy traditionally have been designed manually as expert systems rather than through machine learning. Now, machine learning is distinct in that it uses computers to learn directly from data without utilizing first principles. So you could say that that machine learning model learns much like humans would as children, right? We observe the world around us, we form correlations, we identify patterns, and we can do this without having an understanding of first principles of physics and mathematics, right? We don't need to know Newton's laws to learn how to catch a baseball. Deep learning is a subset of machine learning. It's associated with neural networks composed of many layers of processing. The more layers there are, the deeper the learning. And each layer is just I won't say simple, but it's a nonlinear processing unit that transforms the data coming into it and then passes that transformed data to the next layer, which transforms it again, et cetera. And in deep learning inherently, because each level transforms its input data into a slightly more abstract representation, the data becomes such that it's not intuitive to the human mind, which is why deep learning algorithms have developed a reputation somewhat of a black box. Now, why is deep learning so popular right now today? In a word, it's the accuracy. For about the last 6 or 7 years, I'd say, deep learning algorithms have surpassed human accuracy in some applications. And that's why industries like, I'd say automotive, probably in the forefront, are pursuing deep learning for applications like autonomous driving. So why is deep learning so popular today? Well, in this day and age, it's really the first time that we have a combination of available computing power, huge amounts of data due to an explosion of devices all over the world, generating data and sharing data we can mine and analyze, including, by the way, a ton of satellites in various different orbits. And we couple that with machine learning algorithms, which in many cases have actually existed for decades. And that's what's enabling the practical applications in many industries. When these applications were, or these algorithms were first invented, decades ago, most of the time we weren't applying enough computing power and enough data into the algorithms to actually make them practical. So that's the biggest change that's happened. Now, machine learning's been deployed in the industry on ground segment applications for several years. It's used by many of the fleet operators for things like telemetry outlier detection to call a human being's attention to anomalous data. It's used for Earth image and Earth sensing data analysis. So that's the geospatial analytics for a broad range of applications, things from agriculture and being able to determine how sustainable your farm is, to business applications like maybe counting the number of cars in a parking lot before a major holiday to make some predictions about the economy. So all kinds of uses there. And recently, we've started to see technology demonstrators actually fly machine learning in space. The European Space Agency, for example, is flying a satellite called FISAT, which does onboard cloud detection. And the problem it's trying to solve is basically if we have an Earth-observing satellite and about half of the Earth is covered in clouds at any given time, that satellite spends an awful lot of bandwidth downlinking images that are not useful. So wouldn't it be nice if we had some edge processing that would allow it to prioritize the downlink? So that's basically the application there. There's been some efforts at NASA as well. I won't speak to this very much because I suspect there's probably members in the audience that know more about these things than I do. At the AAS GNC conference a couple of years ago, there was a paper on a small CubeSat called Seeker that flew a convolutional neural network that was trained to detect and localize Cygnus using images from a camera. that was deployed a couple of years ago. Now, this is a talk for a GNC audience, so let's look a little bit more closely about into the relationship between machine learning and GNC. Now, deploying machine learning in space as opposed to on the ground, it requires pragmatic applications. And I'm going to talk about this a little bit in terms of the DI-KW pyramid, or the wisdom hierarchy as it's sometimes called. So we can ask ourselves the question of what level of the pyramid does or should machine learning live at? If you ask, the Hollywood or the media, they would put it all the way in the top, right, where AI is portrayed as containing some kind of pre-programmed wisdom and accumulating knowledge and figuring out how to do things and then take over the world. But the reality is that the sweet spot today is probably somewhere near the information tier. I'm talking about use things like perception and estimation based on input data. And I'll provide a couple of generic examples to show what I mean. So here's an example that uses deep learning to classify IMU data. Now, in this case, the inertial measurement unit is strapped to a human being, and we break down the states of a person into walking, going upstairs, sitting, standing, and lying down. Now, some of my colleagues at MathWorks developed a deep learning model in MATLAB that actually does this time series classification for you. And based on the input data, figures out what state the person is in. And here you can see that algorithm running based on the data. So that's a signal-based application. Here's a couple more examples from the automotive domain, which I mentioned earlier is kind of leading the charge with these types of applications. On the left, we see object detection and tracking. On the right, we see semantic segmentation, breaking down a landscape and again, different classifications. Now, there's certainly potential use cases for spacecraft GNC. Here's a slightly more future-looking use case. We know that for autonomous lunar landing, we need onboard hazard detection and avoidance. There are, of course, many techniques for designing these types of algorithms, but kind of just for fun, we put together a deep learning crater detector using MATLAB, and also using images and video we got from Pangu, courtesy of University of Dundee and Star Dundee in Europe. Now, is crater detection the right application for deep learning? Maybe not. That is more of an illustrative example. Now, we know that there's new machine learning models and deep learning models coming out all the time from multiple different sources. And relatively recently, a standard called ONNX, which is the Open Neural Network Exchange, has emerged, and something that we support. And this standard is helping engineers work with the different models from the different tools and bring them into the MATLAB environment if they so choose. Now, why would they want to do that, bring the models into MATLAB? Well, it's because evolving AI and machine learning from academia and tech demonstrator type projects into actual production projects involves so much more than just creating and training the model. And the full workflow, all the way from the data pre-processing through deployment onto the edge or maybe onto enterprise or cloud systems, is going to be increasingly important. And we've spent almost 50 minutes talking about systems thinking and the criticality of modeling algorithms as part of the system at the system level. And I think that that's also a critical piece of actually integrating AI. What we will want to do is tie our machine and deep learning models directly into our modeling environment that I discussed earlier. For example, through this image classifier block that can be put into our models, so that they can become a seamless piece of the digital engineering workflow. I think ultimately, not yet, but ultimately, that's what we're going to see. And the ease of integration and deployment is really a key to the productization of that, which is why we're investing and have already invested in code generation capabilities for machine learning models, as well as cloud and enterprise system deployment for ground-based deployments. So the MathWorks approach is we approach the AI challenge by trying to enable engineers and scientists to incorporate AI across their entire system design workflow. And I believe that that's why analysts like Gartner here have named MathWorks for the second year in a row as a leader in the Magic Quadrant for data science and machine learning platforms. Now, the elephant in the room that I haven't talked about yet when it comes to machine learning and deep learning deployment is the verification, validation, and the certification. That's probably the biggest bottleneck today to deploying machine learning on critical systems. And honestly, I do not believe that we've figured out how to do this yet. And this is an area where it looks to me that commercial aviation is actually leading the way here a little bit. There are some working groups, including the SAAG34 and the EuroCAE WG114, that are set up to tackle and address this issue that MathWorks participates in. And EASA, which is the European equivalent of the FAA, also published a concept paper recently that'll give you an idea of where aerospace as a whole is with respect to certification. And you know, while we're making strides, I think there's still a long way to go. So I'm going to conclude this presentation with what I really view as a conversation starter for how we might be able to verify and validate machine learning and deep learning models. One, of course, is testing the probability-based requirements. In other words, feed the model a whole bunch of inputs and verify that the outputs match the requirement. And there is some precedent for doing that in our industry, for example, when it comes to docking requirements, landing requirements, things like that. Now, of course, the crux with machine learning is that the output of the model is only as good as the training data that you train the model with. So I think there's some analysis component of that training data to prove its suitability that'll be required. So this kind of outlines that approach. Now we can go another step, and we can include a sanity checking component on the output of our model. There's also a lot of precedent for that in our industry, right? We sanity check even manually generated algorithms. The advantage is that the sanity checking logic is a fully deterministic algorithm that can be fully tested and certified. So that's the advantage there. And we can even go a step further and design a traditionally designed algorithm running alongside our machine learning model, which may not have the same capability. It probably won't be as accurate. Otherwise, why would you bother having the machine learning model? And that can serve as a more sophisticated sanity check, incorporated into some voting logic to make sure that the outputs of your machine learning are bounded. So again, to summarize the conversation started here, a few approaches might be black box testing to statistical requirements, adding sanity checks, and dissimilar redundancy to bound the outputs. All right, so that concludes the machine learning portion. To summarize, we've talked about systems thinking and how the role of systems thinking is becoming more important than ever for GNC engineers. In particular because of how integrated GNC is with all of the other subsystems on the spacecraft. We've talked about fully realized digital engineering that includes and expands upon model-based design and joins model-based system engineering and model-based design for a fuller picture. And also we talked about AI and how we as GNC engineers should prepare not only for developing the AI algorithms, but also how to actually apply them to production systems and be part of the system especially once we crack the nut of V&V and certification. So thank you very much for your time. That concludes my talk today. Back over to you, Neil.
Yeah, all right. Thanks, Ossie. Yeah, so thank you very much for sharing some of your knowledge and insights into this brave new world of digital engineering as it's applied to GNC. What I'd like to do right now is wrap up this webcast before we move on into the live Q&A session with Ossie. If you're interested, I ask the audience to stay online for the live Q&A, be there in about 2 minutes. Wanted to inform the audience that our next GNC webcast will occur on the 16th of March. Our speaker then will be Jason Everett from Marshall Space Flight Center, and he will cover some aspects of the GNC work that he and his team are performing on the Mars Ascent Vehicle, or MAV. The preliminary title of Jason's webcast is Mars Ascent Vehicle GNC Targeting Routines with Considerations to Flight Software. So looking forward to that. Thanks, Jason. As usual, we're soliciting feedback on this particular webcast and also more generally on this series of NESC GNC webcasts. So shortly, an email will be sent out to the registered audience participants. It'll provide a link to our brief and simple online survey form so that we can collect your feedback. That email will also provide a link where today's recorded webcast can be viewed online in the very near future. I think Daniel put that in the chat, several links in the chat you might find interesting. So look at that. The webcast planning committee is always looking for ideas for future webcasts that would be of general interest to the GNC community of practice. So if you have ideas for other, what you think relevant GNC webcast topics might be, please contact me. So thank you for participating with us today, and I hope you can join us again for our next GNC webcast event in March. And this completes today's GNC webcast, so goodbye for now.